Hello, welcome to module 6. So in this module, we're gonna continue the discussion of input space partitioning technique, but we will focus more on task 2, which is the task that we will choose the combination of the input values. Okay, so let's get started. So the structure for modeling software that we're gonna use in this course, there are many of them. So the first one that we are talking about in this class is input space. And the next one that we're going to talk about is graph. And the last one that we're going to discuss in this course is logic. And we're not going to discuss the syntax level in this class. But each one of them can be applied to multiple level of abstraction of your software. So let's say input space can be applied to any level, but the graph structure can be applied to the source code, the design, the spec, and the use cases, while the logic-based technique will be applied to source, spec, finite state machine, and DNF, while the syntax can apply to different abstractions such as source, model, integration, and input. Okay, but anyway, today we still focus on these input space abstraction. So we're gonna discuss the recap a bit of what we have discussed before. So the benefit of input space partitioning technique is as follows. First, it can be equally applied at any several level of testing, starting from unit tests, integration tests, and system tests. And we're gonna keep using this input space partitioning when we do our exercise on unit testing, and also when we do integration tests and system tests as well. This ISP technique is relatively easy to apply with or without automation. So you can just do it with the manual test, or you can apply it to the automated test as well. And you can adjust the procedure to get fewer or more tests. That depends on how many characteristics that you have and how many blocks or partitions that you have. The last one is that you don't need to know the implementation of the system. You just need the input space and the spec of the software that you are testing. Okay. So let's recap again of what is input domain. So the input domain for a program means all the possible input to that program. And even for a very small program, the input domain can still very large. For example, if you have a string parameter, the input domain of this string parameter can be infinite because the string can be many sizes and you can keep adding a character to the string. So the size of the input domain of this string S can be any number and it's infinite. And testing is about choosing the finite set of the value from this input domain. So although you have the infinite input domain, but when you do testing, you need to select some number of test cases from those input domain. And the input parameters are the one that define the scope of this input domain. Input parameters can be many things. First, it can be parameter to a method in case that we look at the source code at the method level. Second, it can be the data that you read from a file. So any input that come in, like the data from a file or the data from an API, the data from the database can be your parameters as well. The global variable are also considered as one of the input parameters. And the user level input that the user put into the UI or the front end part of the system is also considered as input parameters. So the concept of input space partitioning is we're gonna partition these input domain into regions or what we call blocks. And then after that, we choose at least one value from each block. So when you have multiple blocks, we just need to choose at least one value from those blocks, and then we use them as a representative test value. Okay, so one simple example is here. So if your input domain is alphabetic letter, okay, you have one input parameter of character, and the input domain is all the alphabetic letters. We can select the partitioning by using this characteristic called the case of the letter. And then you have two blocks. Block one, when when the letter is uppercase, and block two is when the letter is lowercase. Okay, so in this case, we have two partitions, and then we can select a representative like A, and for this one, we can choose capital A. So to represent this kind of domain partitioning in a mathematical way, let's define that we have a domain D. Okay, so our domain is D, and we have a partition scheme Q. Okay, the partition Q will create set of blocks, okay, which is called BQ. And in BQ, it includes B1, B2, up to the number of blocks that we have, BQ. After that, we have to check whether our partitioning satisfy the two property or not. The first one is disjointness property. So for the disjointness property, we make sure that the blocks that we have must be disjoint from each other. There is no overlap between all the blocks. So if you do intersection of any pair of block, you must get an empty set, okay, for all the blocks that are not the same block, okay. And the second one is called the completeness. So for the completeness property, when you sum or when you add all the blocks together, you should get the full input domain back. So that is when you union all the blocks in BQ, you should get the domain D back. All right. So the disjointness means you don't have any overlap like this. Okay, no overlap. And the completeness means when you sum up all the, when you sum up all the blocks that you have, you should get the full domain D back. So when we use this kind of partitioning technique, we have some assumptions. So first, we're gonna choose a value from each block, and we assume that each value that is chosen will be equally useful for testing because they already been partitioned using your characteristic. They must have some similar characteristics, and then whatever the value that you choose, it should be equally useful, equally the same. And when we apply this to testing, we start by finding the characteristic in the input. Either it's going to be parameter or it's going to be semantic of the program that you are testing. And then you partition each characteristic and you get the blocks. And then we choose a test by combining all the values from the characteristic. Okay. So some example of the characteristic can be as follow. Input X is now or not, and then you can have the block true and the block false. The second one is order of the input file F, and then you have the block of sorted, inverted, sorted, arbitrary, and so on. You can have a characteristic that say mean separation of the two aircraft, and then you have the block of, let's say, less than 1, more than equal to 1, let's say 1 meter. Or can be input devices, and then you can have the block of DVD, CD, VCR, computer, and so on. This kind of partitioning is, let's say, it's not difficult, but sometimes you can get it wrong pretty easily. Okay, so I show you an example here. If you have a characteristic called order of elements in list F, we can have these three blocks. The first one is we try to sort the array. We have the array sorted in ascending order. The second one is we have the array sorted in descending order. Okay, so ascending is low to high. Descending is high to low. And the last one is sorted in arbitrary order. Okay. But this one, when we check for completeness and disjointness, we can see that there are some problems with it. So if you have a list of length 1, okay, if you have a list of length 1, can we say that it's sorted in ascending order, or is it descending order, or is it in arbitrary order? We cannot really tell. So with this kind of list of length 1, it will fall into all the 3 blocks, and then you would violate the disjointness property. So we can modify the characteristics. So what if we say that um, we're gonna change the characteristic to be as follow. So we're gonna decrease it to be only, we're gonna expand it to have 2 characteristics. The first one is list F sorted ascending or not, and then you have the block of true and false. And then characteristic C2 is list F sorted descending or not, and then you have the block B1 and B2 as true and false again. With this, when you separate the characteristic, you can see that they are disjoint because they cannot be sorted ascending while sorting as descending at the same time. And this is also disjoint because if you sort as descending, you cannot sort as ascending at the same time. So by modifying the characteristic or by changing the characteristic, you can avoid those kind of disjointness and completeness properties. This is an important thing. So when you create the characteristic, make sure that you check for completeness and disjointness and modify the characteristic accordingly. So what are the properties of the partition? So if the partition is not complete or it's not disjoint, that means you have not been carefully reviewing the partitions enough. And when you found a problem, you should also try to think about other different alternatives. And in this kind of input domain modeling, we have 5 steps that we have to follow. So step 1 and step 2, we're gonna move from the implementation level to abstraction level. So we're gonna work on input space partitioning at an abstraction level. In step 3 and 4, you work totally on the abstraction level. And in step 5, we're gonna come back down to the implementation level. What does it mean? So let's see here. So step 1 is we identify testable function. So we are transitioning from implementation level here, implementation level. We find all the parameters. This is still implementation level. And then we move to abstraction level. Abstract, sorry. After we know the function, after we know the parameters, we do not care about the implementation anymore. So you just model the input domain based on the parameters that you have. And then you apply the test criterion to those combinations of value. So this is independent from any implementation that you have. And lastly, you come back from the abstraction level into the implementation level again. When you refine the combinations of those blocks, and then you create the test input. Okay, so when you come back to find the value of the test input, then you come back to the implementation level. The step 4 that we're gonna focus on today is how do we choose the combinations of value. One characteristic, once the characteristic and partition are created, then when you try to get the test case value, you need to find some combinations of multiple blocks from multiple characteristics. So how we do it? We're gonna have multiple criteria to help us to find the effective subset of these test case value. Okay, so the first one, the most obvious and the most intuitive one is called all combination coverage. Okay, all combination criteria, sorry. So all combination or ACOC means we're gonna choose all the combinations of the blocks from all the characteristics that must be used. So for example, if you have the number of blocks in all the characteristic, the number of tests that you would have is the multiplications of all the blocks that you have in each characteristic. So let's say if you have characteristic C1, 2 blocks, sorry, characteristic C2, 3 blocks, and characteristic C3, 4 blocks, you would have the total number of tests as 3 multiplied by 4, 2 multiplied by 3 multiplied by 4, and then you get 24. Okay, so let's see some example. If we have this triangle method again, okay, the triangle method is the method that decide whether this given 3 sides, side 1, side 2, and side 3 is a triangle or not. It will return the value of the type of the triangle, scalene, isosceles, equilateral, and invalid triangle. So if we apply the ISP criteria of all combinations on this problem, we have the following characteristics. Okay, so we have 3 characteristics. The first one is side 1 greater than 1. So this is side 1. This is side 2. And this is side 3. Side 1 greater than 1, equal to 1, equal to 0, and less than 0. We have the same for side 2 and the same for side 3. Okay, this is called the refinement of the characteristic, because if you look at the previous video when we discussed this problem, we need to solve the disjointness problem. So we refined it to have no disjoint between all the 4 blocks. Okay, but let's say we have 4 blocks for each of them. So this is 4, this is 4. Let's say I'm gonna just call them A1, A2, A3, and A4, and B1, B2, B3, and B4, C1, C2, C3, and C4. Okay. The value of the each block I choose 2, 1, 0, and -1. They are the same for all the 3 characteristics. Okay. Totally, what we have is that we're gonna have 4 by 4 by 4, which is 64 tests for the triangle method. And this is quite a lot. Possibly it is more than we need. Okay. And what we have are actually not a very good one as well, because we can only have the 8 test values that are actually valid triangle. So the 8 test cases that have valid triangle are the following. And the rest are just not triangle. So we put too much on the not triangle side, and we have only so little of the valid triangle side. So this technique is just a very naive and basic technique that you can just find all the combinations. Okay, but at least if you don't know what to do, you can use ACOC to generate the test cases. Okay, the second one gives you too many test values. So we have the second criteria called each choice coverage. So for each choice coverage, we have the idea that what about we just select at least one value from each block? So each choice coverage, or ECC, we're gonna select, sorry, one value from each block for each characteristic to be used in at least one test case. Okay, and the number of tests is the number of blocks in the largest characteristics. For example, if we still follow the same test cases that we have, I mean the same characteristic that we have C1, C2, C3, and then you have 4 blocks, A1, A2, A3, A4, B1, B2, B3, B4, C1, C2, C3, and C4. So when we choose this combination, we're gonna select just one characteristic, at least one character. We select one characteristic from each block to guarantee that it used at least once. So from all the possible combinations, we reduce it to be only 4 test cases, which is equal to the size of the largest characteristics. I mean, all of them are the same, which is 4 blocks, right? So we'll get 4 test cases. And how do we choose them? So for the first one, I select A1. So this one is used. I select B1. This one is used. I select C1. So this one is used. The second case, I select A2. So this one is used. B2. This one is used. C2. This one is used. I select A3 for the third one. B3 and C3. And lastly, I choose A4, B4, and C4. So with these 4 test cases, we can see that it already used up all the value here, and each value will be used at least once in each of the test cases. Okay, and then we get this value, test case value. So this is test case 1, this is test case 2, this is test case 3, and this is test case 4. Okay. So by using these each choice criteria, we can reduce the amount of test cases a lot, from 64 down to only 4. Okay. The next criteria is called pairwise criteria. Pairwise criteria try to get a little bit more test cases, because the each choice coverage sometimes give you too few tests. Okay, it's cheap, but it might not be totally effective. So we try to find the combination by getting all the possible pair. This is called pairwise coverage. So for the pairwise coverage, a value from each block for each characteristic must be combined with a value from every block for each other characteristic. The number of tests that you would get will be the product of the 2 largest characteristics. Okay, so let's say we have the same table again. Actually, I should copy the table here, but anyway. So we have C1, C2, C3, and we have 4 blocks, A1, A2, A3, A4, B1, B2, B3, B4, C1, C2, C3, C4. The product of the 2 largest characteristic here is 4 by 4, and then you get 16. Okay, so let's see how it works. This one is selecting from the pairs. So what are all the possible pairs here? We need to get all the possible pairs first. So let's write it down. When we think about pairs, it means we are trying to match one block to all the other blocks, like A1, B1, A1, B2, A1, B3, A1, B4, A2, B1, A2, B2, A2, B3, A2, B4, so on and so on. Okay, so I'm gonna write it down. Okay, that's a lot. Let's say A1, B1, A1, B2, A1, B3, A1, B4, A2, B1, A2, B2, A2, B3, A2, B4, A3, B1, A3, B2, A3, B3, A3, B4, A4, B1, A4, B2, A4, B3, A4, B4. And then we have B and C now. B1, C1, B1, C2, B1, C3, B1, C4, B2, C1, B2, C2, B2, C3. Oops. B2 C4, B3 C1, B3 C2, B3 C3, B3 C4, and B4 C1, B4 C2, B4 C3, and B4 C4. So these are all the pairs that we can get from these three characteristics with each four blocks each. And when we picked the pairwise coverage, we must select a value from each block that combine with a value from every block. What it means here is that we need to select to cover all the pairs that we have. So let's say this one. Let's look at the first one. We pick A1, B1. Okay, A1, B1 would select this one. And we also select B1, C1. So we already selected this one. So we keep doing this. A1, B2, B2, C2, B2, C2, A1, B3, B3, C3, A1, B4, B4, C4. Next, I move to A2, B1, B1, C2, B1, C2, A2, B2, B2, C3, A2, B3, B3, C4, A2, B4, and B4, C1, A3, B1, B1, C3, A3, B2, B2, C4, A3, B3, B3, C1, A3, B4, and B4, C2. Okay, we still have a few pairs left, which we hope to be get rid of by the rest. Okay, so A4, B1, A4, B1, B1, C4, B1, C4, A4, B2, B2, C1, A4, B3, B3, C2, and A4, B4, and B4, C3. So you can see that by having 16, sorry, by having these 16 pairs, we have covered all the pairs here that we have generated from all the blocks in all the characteristics. So this is the key of pairwise coverage. You cover all the pairs that are generated from all the blocks in all the characteristics. With this, we get slightly higher number of tests, 16 compared to each choice coverage, which is 4, right? But not as many as the all combination coverage, which is 64. The next one is the extension of the pairwise. It's called T-wise coverage. So instead of just fix the amount of combinations to 2, we can increase it to be any number that is larger than 2. Okay. So T-wise coverage is a value from each block of each group of T characteristic must be combined. Okay. So by doing this, the amount of tests that you have is the product of the T largest characteristics. Depends on what are the size of the characteristic and how many characteristic that you would choose to form the T-wise pair, the T-wise pair. Okay. But if you do all the characteristic, if the T is equal to all the characteristics, then you get back the all combination coverage. Okay. However, this T-wise criteria is very expensive and it's not show very strong benefits compared to the pairwise one. So I think we're not going to discuss it in this class. Just so you know that there is also a T-wise coverage criteria. Okay. The next one is called base choice coverage. So for base choice coverage, we put in some knowledge that we know some of the test value are more important than the other. So we put the domain knowledge of the program into account here. The concept of base choice coverage is that you select a base choice first. So you select a base choice block for each characteristic. And then a base test is formed by using those base choice for each characteristic. And then the subsequent tests will be chosen by holding all but one choice, okay? And using each non-base choice in each of the characteristic. What does it mean? Let's see. So in this case, you're gonna get the number of blocks equals to 1, which is the base choice, plus the sum of the number of block minus 1 for each of the characteristics, okay? So if we have the same characteristic again, C1, C2, C3, and you have A1, A2, A3, A4, B1, B2, B3, B4, C1, C2, C3, and C4. We're gonna have 1, the number of tests is 1, plus the sum of the size of each block minus 1. So this one is 4 minus 1 plus 4 minus 1 plus 4 minus 1. So we're gonna get 1 plus 3 plus 3 plus 3, which is total of 10 tests. Okay, so let's see. We start by selecting the base choice first. So I put some domain knowledge here. I want to select the base choice, which is a valid triangle. 2, 2, and 2, because the choice of A1, B1, C1 here is when the value of the three sides are positive and they are more than 1, okay? So if I already chose this base choice, the next one is I just select the subsequent test by basing on this base choice, but I flip one bit at a time. So for example, I do the second one. So let's focus on this second one. I keep A1, B1, and I flip C2, C1 to be C2. The next one, I keep A1, B1. I flip the last one to be C3. The third one, I keep A1, B1. I flip the last one to be C4. The next one, I flip the second bit to be B2, B3, and B4. And the last one, I flip the first bit to be A2, A3, and then A4. So the number of tests that we have, these are 9, and this is 1. So totally you get 10, as we already computed here. Okay, so the base choice coverage is good when we know that there are some good base test cases, and then you can apply just by mutate or changing one of the block at a time from that base choice. One thing to note about it is that the base choice that you choose must be a feasible test case. Okay, if you select the base choice that is infeasible, then the other derived test cases might also be infeasible. We can choose the base choice based on many criteria. So the first one is it might be the base choice because it is the most likely test that will be input from the user's perspective. It might be the simplest one, or it might be the smallest one. It might be the first in some kind of ordering. So you should have some reason why we choose this kind of base choice. One good suggestion is that you can select the happy path that become the base choice. Happy path mean the one that produce the output as expected. Input that produce the output as expected, the normal output. Okay, so it's the one that you consider very basic flow in the program and the basic output that you should get. You not consider some of the corner cases, some of the exceptions, some of the wrong invalid values. We pick the one that the easiest one, the one that is the program is written for and is supposed to work in the most normal way. Okay. So in this base choice coverage, the base choice is a crucial design decision. And when we select the base choice, we need to document why we select them as a base choice. The last one for the module today is the criteria called multiple base choice. So for multiple base choice, we expand the concept of the base choice coverage to cover more than one possible base choice. So the definition of the multiple base choice coverage is at least one and possibly more base choice blocks are chosen for each characteristic. The base tests are formed by using each base choice for each characteristic at least once. And then the subsequent tests are chosen by holding all but one base choice constant for each base test and using each non-base choice in each other characteristic. Okay, the number of tests that you would have, let's say you have m base tests, and the number of block that is used from each of the characteristic is lower m. Okay, the amount of base choice that we would have is that the number of base tests plus the amount of remaining blocks in each of the characteristic multiplied by the number of base choice. Okay, we're gonna try with the existing example again. So if we have these three characteristics, C1, C2, C3, with the four blocks, A1, A2, A3, A4, B1, B2, B3, B4, C1, C2, C3, and C4. Okay, let's say I pick two base choices now. I pick A1, B1, C1, and A2, B2, C2. So the number of tests that we will have is 2 plus the amount of base choice that is used from the first block. So I selected A1 and A2. So from these four blocks, I have selected already two blocks. So 4 minus 2 plus the second one, I select B1 and B2. So this is also 4 minus 2. And the last one, I pick C1 and C2. So I also 4 minus 2. So this is 2 plus 2 plus 2 plus 2. And then you would get 8. Oh, sorry. It's multiply. I forgot to multiply. So you should also multiply by 2, multiply by 2, and multiply by 2. So what you're supposed to get is you should get 2 plus 2 plus 2 multiplied by 2 is 4, 2 multiplied by 2 is 4, and 2 multiplied by 2 is 4. 14. Okay. We select two base choices, A1, B1, C1, and A2, B2, C2. So based on these first base choice, okay, we're gonna derive the subsequent test. So I keep A1, B1, I flip C2. I keep A1, B1, I flip C4. I cannot select C2 because C2 is already used here. Okay, so this constrains the amount of blocks that we can choose. Then I keep A1 and C1, I flip B2. I keep A1 and C1, I flip B4. I also cannot use B2 here because B2 is already used in another base choice. I fix B1, C1, I flip A3. I pick B1 and C1 and I flip A4. The next base choice, A2, B2, C2. I hold A2, B2, I flip C3. I hold A2, B2, I flip C4. I cannot use C1 because C1 is already used in the base choice here. Similarly, I hold A2, B2, I flip B3. I hold A2, B2, I flip B4. And the last one, I hold B2, C2, I flip A1 to be A3. I hold B2, C2, and then I flip A4. So with this, we get two base choices. And from here, we get 12. And totally, we have 14, just like what we computed. Okay. So this is what we have discussed. So I started with the combinations that will be chosen for ISP technique. The first one is called all combination coverage, or ACOC. And then the ACOC will subsume the multiple base choice coverage, and it also subsume the T-wise coverage, because ACOC is the largest one, right? The multiple base choice will subsume the base choice, because the base choice is just only one base, and multiple base choice have multiple bases. The T-wise coverage subsume the pairwise coverage because it expands beyond just two. And the last one is the each choice coverage will be the smallest one that subsumed by the base choice and the pairwise coverage. Okay, so to summarize, the input space partitioning that we discussed since previous module, it is an easy technique to apply even without any kind of automation. It is a convenient way to add more or fewer tests, depends on number of characteristics, number of blocks, and the combination criteria that you choose. It can be applied to all the level of testing, starting from unit tests, integration tests, system tests, and so on. And it is a technique that based only on the input space of the program, and we do not need to rely on implementation. So it's a simple, straightforward, effective, and widely used technique. And this is all for the concept of ISP, and it is all for this module as well. See you in the next module.